So day 2 of 10-1 polygons. Yesterday I just kind of had you working in groups, measuring the angles, getting an idea of what the angles are, and again some of the names like heptagon, maybe you had forgot that one, or dodecagon, or n-gon, the newer one. But it would probably help if we actually had some kind of definition for what a polygon actually is. And remember, it's very infrequent that I will actually make you give me a definition verbatim. Because I want you to be able to understand the words, and sometimes putting it in your own words makes it a whole lot easier. So once I show you this one, we'll go from there. It's a closed figure. Do you agree with that? That a polygon should be a closed figure? Okay. Formed by a finite. What's that word, finite? Yeah, not unless they're countable, because infinite is the word you're probably used to. That's just a prefix in front of finite, believe it or not. So by a finite number of coplanar. What's coplanar mean again? On the same plane, and do you agree they should be on the same plane and be segments? So coplanar segments such that. I'll give you 2 situations that should happen. They might seem silly, but they actually, once you think about them, they're pretty good. And once again, you can paraphrase it once we talk about it, so you don't have to write it perfectly. So number 1 says that the sides that have common endpoint are non-collinear. Ooh, that's a big word. Non-collinear, what's that mean again? Not on the same line. Basically what that means is you shouldn't have a polygon that does something like this, a point there, a point there, a point there, a point there, a point there. Does this point right here, is that a common endpoint for that side and that side? Is that common? Yeah. Is that collinear though? Yeah, it is. See how that's all on the same line? What they're saying is, that's no good. All right. Now, if I got rid of that point, would this be a polygon? Yeah. This next one says each side intersects exactly 2 other sides, but only at their endpoint. Does this green side right there connect to only 2 other sides? Yeah, it does. And it only does it at their endpoints. We'll get rid of that point that we said was no good. There you go. So what does it mean that it only connects at their endpoints? Well, what it's saying is you can't do that. Because is that green one, well, now it's hitting a whole bunch more, isn't it? Okay, can I do that? Is that legal? No, you can't go across like that. That's what it's saying. Okay. So for this first one, you could probably say there has to be some angle there other than 180 if you want. And for the second one, you could say just make sure it goes around the outside or something like that. That would be fine. Okay. Those are all good. Because I think most of us have a pretty good vision in our head of what a polygon is. Okay. And I think that first one's pretty good. Closed figure, finite number of coplanar segments. That's pretty good. Okay. Convex polygon. Well, let's get it right up there. So it's got to be a polygon. So in other words, it's got to be a closed figure, finite number of coplanar segments. Now, this is one that I'm definitely going to paraphrase for you. This is the book's definition, where if the sides were turned into lines, the lines would not hit the inside of the polygon. What? Here's what they're saying. And then we'll paraphrase it. They're saying if I turned that into a line, would any of those go on the inside? No. How about if I turn that into a line? Do any of those go on the inside? No. How about if I turn that into a line? Do any of them go inside? That one? No. And we'll just pretend those 2 crisscross ones aren't in there. Does that agree? Yeah. Here's kind of how I look at it. For convex, I say that it doesn't cave in. That's what I say. Because does that cave in at all? No. Okay. I love this one. This is the actual book's definition right here. A polygon that is not convex. That's just brilliant. So in other words, the lines would go on the inside. Okay, so here's how I look at it. This one here caves in. This one does not. That's how I look at it. So for example, would you say that one caved in? Yeah. And watch what happens. Well, does this line, if I extend that into a line, does that go on the inside? How about this one? Well, then what's the problem? This one? Oops. Oops. How about this one? Oh, okay, if I would have hit it, that probably would have been better, but yeah, that one. So here's how, again, how I look at it. Caves in, doesn't cave in. Pretty simple. There is. Imagine if somebody were to walk in right now. That would be very, very confusing. But I think you get it, don't you? My insanity there. Determine if the following polygons are convex or concave. So what do you think? If I turn these, well, what is this? A 1, 2, 3, 4, 5, 6 sides. What's that called again? That's a hexagon, right? Okay. This black hexagon that we have on the left side here, would you consider that convex or concave? If you made those into lines, would it ever go on the inside? Nope. So I would consider that one convex. You do not have to write your answer on the inside. That is just what I chose to do. How about this one over here? Kind of reminds me of that first aid symbol. Is that convex or concave? Concave, yeah, it caves in a bunch of times. That's definitely concave. What's that one called? Concave, but if you had to do it by numbers, I believe there are 12 sides to it. It's a dodecagon. Even though it's concave, it's still a dodecagon? Yeah, it still has 12 sides. All right. Is it still a polygon? This green one? Is it a closed figure? Yeah, finite number? Yeah, it still is. We're just kind of breaking them up into little divisions, convex or concave. So why don't you go ahead and discuss the blue and the red one right now and decide if you think it is convex or concave for those. All right, so one of these was meant to be somewhat of a trick question. It sounds like somebody caught it. This blue one on the left, how many sides we got there? 1, 2, 3, 4. So that blue one on the left is a pentagon, and is it a concave pentagon? Most definitely concave, caves in big. So concave. How about this red one over here? Well, it all depends on what I want you to look at the entire thing as an object. And if you do that, is it convex or concave? Technically, neither. Because that whole thing right there, if you look at it all together, not a polygon. If you look at the two triangles separately, well, you have two polygons, and those two separately would be convex. But this is breaking that rule where that point, and that point are on a line. Big breaking of the rules. All right. And then we're going to talk about this blue one here quick at the end here. But down here it says the exterior angle theorem. Based on what we did yesterday, you should be able to fill in that blank. It says if a polygon is convex, very important, then the sum of the exterior angles, one at each vertex, yesterday, one exterior angle at each vertex, what's the sum? 360. Does it matter how many sides there are? No, it does not. We did an octagon yesterday, the sum was 360. We did a triangle, the sum was 360. It didn't matter. The only other thing I want to talk about on this blue one is these letters here, obviously, are where the points are. And what do you suppose those points are called? Endpoints or vertices, right? When you name a polygon, can you just jump all over the place? Where can you go like A, D, C, E, B? Can you do that? No. What you have to do is go in order, either clockwise or counterclockwise. Doesn't matter to me. Yeah, I noticed that. That's all right. Most people aren't going to notice. The comment was made that in the red one I missed the Y for polygon, and yes, I did. It's okay. But this one over here, could I list this as polygon, say A, E, D, C, B? Even if it's not in alphabetical order, that's okay? Yeah. But you can't just jump all over the place. Can I start at C if I felt like it? Yeah, as long as you go in one order or the other, it's fine. And where you start really doesn't matter. Do most people try and do it alphabetical? Yeah, this is the way most people are. Yeah, make sure when you spell polygon, you do it right. Okay, so right now what we're going to do is I gave you a bunch of objects. We're going to fill in this chart right here. It is on the back. I think we should be able to fill in the first column right now for a triangle. How many sides are there? 3. There are 3 sides and 3 angles. Imagine that. Quadrilateral. How many sides are we looking at? 4, followed by? Not a trick question. 5. Hexagon. Did I skip the 7 this time? Nope, there it is. Heptagon, 7. And octagon, 8. Please refer to the spelling of octagon. It's an A, not an O. Thank you. All right, now, what we're looking at here is I'm going to show you how many triangles can be made because we're going to try and figure out that formula down at the bottom that some of you may remember from middle school. In a triangle, basically, here's what I want to do. If I go from each vertex, I want to connect, start at any vertex you want and make sure you connect it to all other vertices. So if I start here, am I connected to that one? Am I connected to that one? So am I already connected? If I start here, am I connected to all other vertices already? So how many triangles are there? One. All right, there's one triangle there. How about that? So how many triangles? One. What's the sum of those measures again? You can look at yesterday's notes if you want. We already did that, right? For a triangle, the sum is 180 for a triangle. Yeah, one angle would be 60, but this is saying the sum of the angle measures is 180, right? In phase, can't most of you probably tell me this next one before we even do anything? This one's 360, right? But let's go and find out how many triangles are in that thing. Where's the quadrilateral here? Oh, it's the red one. Again, you pick any vertice you want. Oh, right there. Did I connect that one already? Yep. Did I connect that one? Did I connect it to all? Not quite yet. How many triangles are in there? 1, 2. And do you agree if I take that angle plus that angle plus that angle, that would be number 2 triangle? And then if I take this angle over here and that angle there and that angle there, that'd be number 1 triangle, correct? And if I add both triangles together, I would actually get all the angles of that quadrilateral, wouldn't I? And so notice if there are 2 triangles, does it make sense that it's 180 each, so the total is 360? Oh, it does. How about that? All these things making sense are just amazing. There are 2 triangles there. Everybody see where the 2 triangles were? Right? 1, 2. So the next one's the pentagon. Again, on yesterday's notes, do you already know the total for that? Remember, pentagon was kind of that weird one for one angle, right? But we know that. But let's just pick one. Which one do you want to do? Which vertex should we pick? Top one. All right. Is it connected here? Yep. Connected there? Is it connected to that one? Well, now it is. Connected to that one? Yeah. How many triangles? 1, 2, 3. Once again, if I take all these angles into consideration, do I actually get all the angles of that pentagon if I add them all up? So let's go back, and we're talking about how many triangles there? There are 3. Now, wait a minute. Each triangle is 180, right? 180 times 3 is 540. Is that what you found out yesterday with our little exploration we did? That's exactly what you found. I would like you to try and finish this little table right now. And then I would like you to look for a pattern. All right, you may notice that I was trying to be a little tricky again. I'm just seeing if you're paying attention. Hexagon. Is there a hexagon back there? Oh, hey, there it is. And does it matter which one you start with? Not really, but you connect them all. And how many triangles are we looking at? 4. All right, well, let's just remember that there's 4. 1, 2, 3, 4. We're just a little short on time. And this one here's the octagon. Where's the heptagon? Yeah, not drawn. I was just paying attention. So you draw this in. How many? 1, 2, 3, 4, 5, 6. All right, so let's go back and see if we can figure this out. So we just found out that this one has how many? The hexagon has 4. This one down here, the octagon has 6. So wait, this is 4 triangles. So 4 times 180, right, is 720. And then down here you take 6 times 180, right, because that's how many triangles there are. And did we get 1080 yesterday? Isn't that what we got? Well, with that in mind, can you find a pattern here to figure out heptagon? Yeah, if there's 7 sides, how many triangles are there going to be? 5. That's because you've already connected 2. You only have to connect the other ones to make 5 triangles. And then you take 5 times 180 and 900. And I believe that's the only one right there that we didn't write down yesterday, was that it was 900. Now, the whole idea here is to find a pattern. We know to take the number of sides, and you notice if you take away 2 every time, it tells you how many triangles are there, right? And so if I know a triangle is 180 every time, the formula is take the number of sides, which is n, minus 2. Do you agree that should give me a number every time? All right, and obviously if I start with 3, 3 minus 2 is 1, and you can see that right in our chart here. And whatever that number is, basically all I did is I took it times 180, right? The reason is that right there is basically how many triangles will be in there, right, that part, and this is how many angles a triangle, or how many degrees a triangle has. So does that make sense? I sure hope so.